So we're going to learn how to graph systems of linear inequalities. So far, all we've graphed are systems of equations, which generally just have one solution. There's one spot where the two lines cross. Inequalities, as you may recall, is when you graph a line, either dotted or solid, and then you shade above or below the line. So a single inequality has many, many solutions. And we're going to do a system of inequalities, um, which means we're going to graph and then shade for two different lines. So in order for us to be able to um, graph these, either using Desmos or using a graphing calculator, we must have the inequalities in slope-intercept form. And both of these inequalities that we are starting off with right here are in slope-intercept form. We've got y equals, or in this case, y is greater than mx plus b. And down here on the bottom, we've also got mx plus b. So both of these to start off with are already in slope-intercept form, which is fantastic. It means we're ready to graph them. So I'm going to use Desmos for the demonstration today. So I'm going to slide over to Desmos. And I'm going to put in the first inequality, y is greater than. On the Desmos calculator, it has the greater than, or equal to symbols right here, or you can just use the key on your keyboard to do it. Negative 2x plus 1. And so as expected, we've got our line with the shading. It is greater than, so it's shaded above the line. And because it's greater than and not greater than or equal to, it is a dotted line. So anything that is in this shaded area right here is a solution to this inequality. Let's go ahead and put our second one in there, which is y is less than or equal to x plus 3. And there's our second one. I'm going to move the first one out of the way for a second so we can look just at the second one. This one was less than, so it's shaded below the line, and it's less than or equal to, so that's why this line that we have here is solid. Now, the solution to a system of equations was the spot where the two lines intersect. The solution to a system of inequalities is where the shading intersects. So our shading intersects in this purple area right here. So anything in this purple area would be a solution to our system. The red area is not, and the blue area is not, because that's where the shading is for just one of the inequalities. It's the shading for the purple area here. That is the spot where we've got our solution to both inequalities. So there's a lot of answers, anything in the shaded area. Okay, let's take a look at a different one. Let's look at this. Y is less than or equal to 3, and x plus y is greater than or equal to 1. So they do have to be in slope-intercept form, and this one already is. Y is less than or equal to 3 already has the y isolated, so that is in slope-intercept form. The bottom one is not. We have to do a little bit of algebra on this bottom inequality to get it in slope-intercept form. One step will get this in slope-intercept form, and that one step is to subtract x on both sides. So minus x, and we'll have y is greater than or equal to negative x plus 1. And so now that inequality is in slope-intercept form. So the two that I'm going to be graphing are y is less than or equal to 3, and y is greater than or equal to negative x plus 1. So those are the two inequalities that I will be graphing. So I'm going to go back to my graphing calculator. Y is less than or equal to 3 is, of course, just a horizontal line. It's less than, so it's shaded below the line. And it's less than or equal to means it is a solid line. And then the other one is y is greater than or equal to negative x plus 1. There's the second part. And the solution to this system of inequalities is anything that is in this really dark part here where the shading overlaps. So like positive 2 zeros an answer, 4 zeros an answer, 4 2 is an answer, 6 2 is an answer. Any coordinate that is found in this shaded section here is a solution to our system of inequalities. So the hardest part of these is getting the inequality in slope-intercept form. So let's look at one that's quite a bit more challenging than that to get in slope-intercept form. Here's one where neither inequality is in slope-intercept form. So let's go ahead and fix that. Here's the first one. This is not in slope-intercept form. And the fastest way to get this one in slope-intercept form is to subtract 3x on both sides first. So minus 3x and minus 3x. We end up with negative y is greater than or equal to, and I could write 2 minus 3x, or I could keep it in that slope-intercept form and have the mx come before the b like that, negative 3x plus 2. And now hopefully you remember your rules for dividing by a negative with an inequality, which is if I divide by a negative, the inequality symbol flips. So negative y divided by negative 1 is a positive y. My greater than or equal to now becomes a less than or equal to. Negative 3x divided by negative 1 is a positive 3x. And 2 divided by negative 1 is minus 2. So anytime I multiply everything by a negative number or divide everything by a negative number, the inequality sign flips one way to the other. So let's take a look at the second inequality that we have, which is this one. And so just like on the last one, we'll begin by subtracting 3x on both sides. Like so. It'll leave us with negative y is less than negative 3x minus 5. And then we'll divide every part of this inequality by negative 1. So divide negative 1, divide negative 1, divide negative 1. And just like before, because we divided by a negative, our inequality switches, in this case, from a less than to a greater than. Negative 3x divided by negative 1 is positive 3x. And negative 5 divided by negative 1 is a positive 5. So here is our second inequality. So these are the two inequalities that we're going to graph. Y is less than or equal to 3x minus 2, and y is greater than 3x plus 5. So let's slide on over and graph these two. Y is less than or equal to 3x minus 2, and y is greater than 3x plus 5. And let's make this a little friendlier color there. There we go. So you may have suspected when you looked at these inequalities that they were going to be parallel because they both have a slope of 3. And in this particular case, there is no solution to this because there is no spot where the shading overlaps. And our solution is always where the shading overlaps. We don't have any overlapping shading here, so there's no solution. But I don't want you to think that there's no solution just because the lines were parallel, because that is not true. If, for example, I were to change this second inequality from greater than to less than, now they're still parallel, but I do have a solution because there's this spot over here on the right where the shading absolutely does overlap, and so I do have a solution. So just because they're parallel doesn't automatically mean there's no answer. I'm always looking for spots where the shading overlaps. Okay, the last thing I want to talk about is how to decide whether or not the answers you get to a problem are reasonable. So here is a question in which someone is running for student council, and the election rules say that for the election to be valid, at least 80% of the 900 students must vote. So we have 900 students and 80% must vote for the election to be valid. How many students is that? What is 80% of 900? And that will tell us how many people have to vote. Okay, so I'm going to do 900 times 80%. My calculator doesn't have a percent key, so 900 times 0.8 or 0.80, and that's going to be 720 people. So at least 720 people have to vote. The other thing the problem tells me is that the person who is running says she needs more than 330 votes to win. Okay, so let's define our variables here. Let's say X is going to be the votes needed to win. And Y is going to be the total votes cast. Now, what we just figured out was for the election to be valid, the total number of votes cast must be 720. So Y has to be at least, that's greater than or equal to, is at least 720. And the person who's running says she thinks that she needs more than 330 votes to win. So the votes needed to win has to be more than 330. And we may think that these two inequalities are good enough, but they're not. Let's take a look at the graph and see why just these two alone, although they are correct, are not enough. So y is greater than or equal to 720, and x is greater than 330. I'm gonna have to zoom out quite a bit, obviously, to see my graph, because this is in the hundreds, right? So let's zoom way out. Okay, so the overlap is where the possible solutions are. Anything in this area is a possible solution. Here's where we run into a problem. One of the points in this area is 1,000, 1,500. That's this point right here, the coordinate 1,000, 1,500. That is a point in this solution set, 1,000, 1,500. So just these two right here have the point 1,000, 1,500 in there. And this point does not make sense because it says that we defined X as the number of votes she needed to win. So she got 1,000 votes, and Y was the total votes cast, 1,500 voters. How is that possible whenever the problem tells us that there are only 900 people in the school? How could she get 1,000 votes, and how could there be 1,500 voters if there are only 900 people in the school? So we need to come over here and say, why, although it has to be at least 720, it also has to be less than or equal to 900. The total number of votes cast cannot be more than 900. So let's add that in. Y maxes out at 900. Okay, so now everything in the shaded area is okay? Well, let's check and see. It looks like one of the points that's in here is, let's do this point right here. This is the point 800, 900. This means 900 people voted and 800 voted for her. That seems reasonable. What about this point right here? This is the point 900, comma 800. Could that happen? 900, comma 800? Well, the point 900, 800 means she got 900 votes, but only 800 people actually voted. How could she get more votes than there were voters? So we need another inequality to say that the number of votes that she got has to be lower than the total number of votes cast. She can't get more votes than there were votes. So the number of votes she got, X, has to be lower than the number of votes that were cast. X must be less than Y. She can't get more votes than there were votes. So X less than Y. And now this shaded area right here, this part right here in the middle, now this is an accurate area. Any of the points in here any points in this sort of this trapezoid shape, any points in there should be should be accurate. I suppose we should change this to less than or equal to, because although it is unlikely, less than or equal to means she might get every vote. We can do less than or equal to if every single person who votes for her. If she gets 100% of the vote, it could be equal to. So this point, 900 means everybody votes and they all vote for her. This point, 720 means the minimum number of people vote, 720, but they still all vote for her. Now, these points down here aren't good for her. This means 900 people voted, but she only got 330 votes. See how it's on the dotted line? That is not in the solution set because she said she needed more than 330 votes. So this would not be a guaranteed win. Neither would this. This is the minimum number of people voted, 720, and 330 voted for her, and she said she needed more than 330 to win. So it'd have to be maybe 331 and 720 for her to win the election. Okay. And so that is how you take a word problem, get the answers, and then check to make sure that your answers make sense.